Complex and detailed wrinkles are a fundamental feature in the world around us. A key feature of these wrinkles patterns are Y-shaped singularities, where the wrinkles branch and merge. We're circling a few of them here in blue. And of course, these geometries are often not static. The wrinkles and singularities smoothly evolve in time as the patterns change. For example, look at how the wrinkle patterns and their singularities change here over successive frames as we twist this sleeve. We can think of wrinkles on surfaces as displacements applied to an underlying wrinkle-free surface. These wrinkle displacements are, in turn, parameterized by a wrinkle amplitude and phase. In this work, we propose a model and methods to represent highly detailed wrinkles on a coarse underlying surface and to smoothly evolve them through time for applications in design, editing, and animation. As one example, here we start with large wrinkles on a thick dress from a cloth simulation. Suppose you instead want a dress made of a thinner, silky material. Using our work, you can generate an analogous wrinkle pattern with double the frequency and half of the amplitude, giving us the dress geometry on the right without resimulation. You can then swipe through a smooth interpolation of the wrinkle patterns to select the desired look. Here, we animate our method's interpolation between coarse and fine wrinkles on the shape. Our paper's main contributions are the complex wrinkle field, or CWF, parameterization of wrinkle patterns, which can encode high-frequency wrinkles on coarse space meshes while supporting the representation of singularities, an algorithm for smoothly evolving CWF wrinkle patterns between two prescribed keyframes, and a CWF subdivision algorithm for rendering high-resolution, detailed wrinkled surfaces expressed in our representation. In the smooth setting, amplitude and phase at every point can represent arbitrary wrinkle patterns. Unfortunately, this representation does not extend in a straightforward way to triangle meshes. As we see here, sampling phase on a coarse mesh undersamples wrinkles with wavelengths shorter than the triangle size, and the resulting wrinkles are badly aliased. To solve this problem, we introduce complex wrinkle fields, which separately encode amplitude and phase on the mesh vertices and frequency on the mesh edges. This extra frequency information allows CWF to resolve fine wrinkles and singularities, even on coarse space mesh surfaces. Our paper includes two core algorithms for working with CWFs. First, we provide an algorithm based on finding a geodesic in the space of inextensible shells for smoothly interpolating between wrinkle patterns through time. And second, we describe a subdivision algorithm for rendering fine wrinkles on loop-subdivided base mesh geometry. Next, we compare our CWF interpolation against alternatives. We start with a simple case of interpolating between two wrinkle patterns on a torus, asking for an interpolant that rotates the wrinkles by 90 degrees. Prior works by Knoppel et al. And Chen et al. Can generate static images of wrinkles, but cannot be used for temporally coherent interpolation, since, as we see here, their output is not continuous in time. On the other hand, a simple baseline, constructed by linear interpolation, is temporally coherent, but produces highly non-geodesic paths through the space of shells with many unacceptable artifacts. Our CWF interpolation is the only method which achieves both spatial smoothness and temporal coherence, with singularities merging, splitting, and sliding over the surface. Next, we compare interpolation behavior on surfaces with more complex geometry, like the Stanford bunny. Notice that in this case, Chen et al.'s result has an additional artifact. Singularities entirely fail to appear during the wrinkle interpolation. In this final comparison, we specify a very large and local increase of wrinkle frequency at the top of the phantasma model. Once again, Knoppel et al. And Chen et al. Generate temporally incoherent interpolation, and likewise, Chen et al.'s result is missing singularities. Only our approach generates spatially smooth and temporally continuous wrinkle interpolation, with smooth sliding of the singularities. Next, we compare our upsampling algorithm against baselines. Chen et al. Describe a method for loop upsampling phase and amplitude to achieve wrinkle rendering, but unfortunately, their limit surface misses singularities. Zoenko and Harders also introduce a method for upsampling wrinkles based on interpolation smoothing, but their results introduce non-smooth artifacts. We next compare to several alternatives for upsampling phase alone. Ignoring the noticeable base mesh artifacts, they both also fail to produce a smooth phase field near the singularities in the phase pattern. Our paper presents several applications of our CWF representation and algorithms. Users can add wrinkles to surfaces by specifying a few guide vectors and amplitudes. They can also edit wrinkle patterns by specifying local changes in wrinkle orientation, amplitude, or frequency. In this first example, we show the interpolation of wrinkles on a cylinder, where the initial wrinkles are regular circumference patterns, and the final wrinkles are obtained by rotating wrinkles on a local patch, marked in red, by 90 degrees. Here, we animate the interpolation. Notice that although the wrinkles start out quite regular, even this simple local rotation requires singularities to be created and moved in order to smoothly evolve to the final pattern. Our pipeline also supports more detailed and complex control of wrinkles via editing, while still generating smooth wrinkle interpolation. Again, spatial smoothness and temporal coherence are maintained with singularities merging, splitting, and sliding over the surface, as we see here. Please see our other supplemental videos for more examples and evaluation. Thank you.